So let's next talk about equilibrium compositions and the equilibrium constant. K is what we will call the equilibrium constant, and it's defined as the negative change in Gibbs energy divided by RT. And this change in Gibbs energy is what happens across our reaction. So the stoichiometric coefficient times the partial Gibbs energy of all of my products minus the same for all of my reactants. If you combine these and use laws of exponents and putting the chemical potential into terms that make more sense to most of us, I can get this form here, which is complicated looking, but really not so much. The mole fraction of my products raised to the power of their stoichiometric coefficients divided by the same thing, mole fraction to stoichiometric coefficient powers for my products or reactants, times the pressure divided by whatever my reference pressure is, all to the new power, the sum of the stoichiometric coefficients of products minus reactants. Now this is the definition that's valid for gases. I'll have a minor variation here if I'm talking about liquids, and solids are not going to appear in this reaction. So we're not going to be covering those because we're really wanting to focus on combustion type reactions. And so this equation here will be very, very helpful to us. This is the form we need. So let's try seeing how we can combine our definition of how to use extent of reaction to get mole fractions with this equilibrium constant in order to gather the appropriate data. Now we will find that we have data in our data tables for Gibbs energy. It's the same tables that we've been using when we wanted to look up heats of formation and so forth. So I'll be able to look these up, and then based on this plus how these are related to extent of reaction, I can figure out what the actual composition is at equilibrium. So, alright, now this is just one that I happen to already have written up. So it's butene going to butadiene plus hydrogen. Okay, and we're going to feed pure butene into this reactor. I'm going to let the reaction happen at 25 degrees C in 1 bar. That's my reference state, but that's also where I have data tables in the appendix of your textbook. And in this case, delta G naught is going to be the Gibbs energy of hydrogen plus butadiene minus butene. Okay, so reactants get subtracted, products are added. I use stoichiometric coefficients. In this case, they all happen to be 1. And using data out of a data table, I came up with 79.5 kilojoules per mole. Now, that means that the K is the exponential of negative delta G divided by R divided by T. And so I have this number for K. If I then wanted to use this, what I would say is, well, I find it easiest to say I started with 1 mole of C4H8, 0 moles of each of the other 2 substances, so I had a total of 1 mole. At the end, I had 1 minus epsilon of the C4H8. I had formed epsilon of C4H6 and epsilon of H2. So now I have 1 plus epsilon. So my mole fraction is the number of moles of the substance divided by the total moles of my gas. And I have a Y for each of my substances. This I can now use along with the K value. So the K value that I got from using the Gibbs energy data from the data table is the Y of the products divided by the Y of the reactant. Now, at this point, it's just a matter of plugging in those formulas we just had there. It simplifies a little bit to epsilon squared over 1 minus epsilon squared, and I can solve this, and I got epsilon is 1.08 times 10 to the minus 7th, which means really the reaction barely goes. Okay? A couple of molecules might react, not very many. And so we would normally say that this means that these reactions don't occur. But this is at 298 Kelvin. Can we find the information at other temperatures? In order to do that, we would need to use something called the Van 't Hoff equation. Now there are others, but the Van 't Hoff equation says that I can actually, if the delta H for the reaction is fairly constant as I go from temperature to temperature, then the log of the K ratios from temperature 1 to temperature 2 is negative delta H over R times the differences in the reciprocals of the temperatures. And for several different reactions, this is a graph of what the log of K versus 1 over T looks like. And you see that these really are straight lines, very, very little curvature to these. And so the Van 't Hoff equation appears to hold for most reactions. Now if I use this, what it will allow me to do is calculate K1 using Gibbs energy out of the data tables, and then delta H for my reaction can then get me to the K at a different temperature. And that's important because sometimes what happens at a low temperature, for instance in this butadiene formation reaction, it barely progresses at 298 Kelvin, but let's look at 900 Kelvin. Now delta H for the reaction is 108,000 using heats of formation across the reaction. R is 8.314. My temperatures are 900 and 298. I just calculated that K is 1.16 times 10 to the negative 4. So if I solve this equation for K at 900 Kelvin, I find that it is 0.0534, much, much larger. When I solve for epsilon here, I now find that epsilon is 0.225. So instead of the reaction barely progressing, the reaction now is going to be very substantial. Now finally, what happens if you add inerts? Inerts are molecules that don't actually participate in the reaction. So when we did our combustion reactions, we had nitrogen that was carried along with the air. Nitrogen was an inert, okay? It did not actually participate in the reaction, it just was present. But the presence of these inert substances will change the equilibrium. Sometimes it will make it better, sometimes it'll make it worse. But it's important to include them when we do our calculations. So let's take this reaction one last time and do it at 900 Kelvin, but this time we're going to add some steam, 10 moles of steam for every 1 mole of butene. So before I had 1 butene, 0 butadienes, and 0 H2s in the feed. Now I'm going to also have 10 moles of water. Now water isn't going to participate in the reaction, so I'll have 10 moles when I leave also. Just like our nitrogen, it never participated in the reaction. What came in also came out. But the number of moles of these other things stays the same. Epsilon forms, epsilon is reacted away. But because the total number of moles changes, the mole fraction changes. And when I plug this in here for K, well, the algebra turns out a little different. It's slightly more complicated. I had to use the quadratic formula, but I found that epsilon was 0.535. So the extent of reaction more than doubled, or roughly doubled, I guess, by adding 10 moles of steam. So this indeed was an important contributor to the extent of reaction. This concludes our video lessons for this course.